Jai Hind students, welcome to my YouTube channel. Students, failure doesn't mean the game is over. Instead, it means try again with experience. So, in order to succeed, your desire for success should be greater than your fear of failure. Actually, the true measure of success is how many times you can bounce back from failure.
With that positive note, students, let's begin today's session. Today we are going to discuss a very interesting topic of surface tension. Now, in order to understand this phenomenon of surface tension, it is necessary to have some idea about the intermolecular forces which actually operate to keep the liquid molecules together. Now, students, when the two molecules approach each other, the charges in each are distributed and then redistributed in a fashion that the average distance between the unlike charges in the two molecules is a little smaller than that between the like charges. Thus, electrostatic attraction actually wins over the repulsion and gives rise to intermolecular attractive forces. So, intermolecular forces are basically of attractive nature. And because of the fact that the intermolecular forces are effective only over very, very small distances. They are effective only between molecules, isn't it? So they are also known as short range forces, right? And obviously they do not obey inverse square law. Now students, in order to have a more clear picture of intermolecular forces and the types of molecular forces, we need to watch this beautiful animation.
Intermolecular forces are of two types, cohesive forces and adhesive forces. Cohesive forces are the intermolecular forces that exist between the molecules of the same kind. These are the attractions that molecules can exhibit between one another that cause cohesion in a substance, which can be quite significant for a very viscous substance. In a liquid, these cohesive forces are felt equally in all directions by most of the molecules, but not for the molecules that are at the surface of the liquid. These molecules only interact with half as many molecules as the others because they are at the edge of the substance with no more molecules to one side. This is why liquids tend to contract to form shapes that minimize their surface area. We can see this in a drop of water, which will be roughly spherical. The sphere is the shape that minimizes surface area, so a water droplet will adopt this shape to maximize the hydrogen bonding that is occurring in the droplet, allowing the system to sit at the lowest energy possible. Of course, if this droplet becomes larger, other effects like gravity and air resistance come into play, and it will not remain spherical for long. But in tiny droplet, we can see this effect quite pronounced. The interactions between the molecules of a liquid and some solid surface are called adhesive forces. These describe the ability of a liquid to adhere to that surface. Take water for example. If we place a drop of water on a piece of plastic or some other non-polar surface, then it won't interact with water. The water will not wet the surface and it will maintain its spherical shape. This is because the cohesive forces, the hydrogen bonds occurring between the polar molecules inside the droplet, are stronger than the adhesive forces between the water and the non-polar surface. But if we place a droplet on glass or another polar surface that will interact with water, then it will spread out and maximize interactions with that surface, because in such a case, the adhesive forces are stronger. We can see this happening when we place liquids in a glass tube, like a graduated cylinder. Because water is attracted to the glass, it will form a concave meniscus, meaning that the surface will curve downwards. That is because this configuration will allow water to maximize its interactions with the sides of the glass tube. If we try this again with mercury, it will look totally different. In mercury, the cohesive forces between the mercury atoms are stronger than the adhesive forces between the mercury and the glass. So mercury will form a convex meniscus, which is when the surface curves up like this. It will do so as to minimize interactions with the glass, which in turn maximizes the interactions between the mercury atoms.
So intermolecular forces are basically of two types: cohesive intermolecular force and the adhesive intermolecular force. As we have discussed in the video, that the force of attraction between the molecules of the same substance, that is known as force of cohesion. The force of cohesion is maximum in solids, it is lesser in liquids, and it is least in gases. And it is for this reason that solids have definite shape and resist all the deforming forces. Actually, there are various examples of force of cohesion. The solids exhibit their rigid character and definite shape due to the strong force of cohesion between their molecules. Now also, adhesive force. This is also a type of intermolecular force. It is the force of attraction between the molecules of the different substances. The examples of adhesion are the sticking of glue to the wood or paint to the wall, or for that matter, we are able to write on the blackboard. That is because the particles of the chalk, it basically stick to the blackboard due to the large force of adhesion. And this is the reason we are able to write on a blackboard with a piece of chalk. So these are the two basic types of intermolecular forces. Now students, let us discuss surface tension.
Surface tension is a phenomena which is related to cohesive forces. Surface tension is defined as the energy required to increase the surface area of a liquid. This will depend on the strength of the cohesive forces in the liquid. The stronger the cohesive forces, the stronger the surface tension, as any increase in the surface area will necessarily disrupt some of these interactions. Different liquids have different surface tensions, and water has an irregularly high surface tension considering the small size of the molecule. This is because of the strong hydrogen bonding occurring. Water does not want to reduce the amount of hydrogen bonding occurring by increasing the surface area, and this phenomena is the reason that a paper clip, if carefully placed on top of the water, will float. The paper clip is more dense than water, so it should sink, but the surface tension keeps it afloat based on the strength of all the hydrogen bonds. Many bugs take advantage of surface tension in order to walk across water. They too are far more dense than water. It is the strength of the cohesive forces between the water molecules that supports them. If an object like a bug were to pierce the surface of the water, some of the hydrogen bonds would have to be disrupted, as some of the volume would then be occupied by something other than water molecules. That is why the surface of any body of water can act almost like a stressed rubber membrane. In order to understand surface tension, put small quantity of milk into water. This is actually too fast to see, but watch what happens in ultra slow motion when droplets of milk hits the water surface. Instead of breaking, the water surface stretches, bouncing the milk drop back into the air. Thus, the water surface behaves like a stressed membrane having a tension in all the directions parallel to the surface. This tension in the surface of a liquid is called surface tension. It can be seen that the droplet of milk takes the shape of a spherical drop. It is because for a given volume, a sphere has the least surface area. It means that the surface of every liquid has a tendency to have a least surface area, and in this respect, it behaves like a stressed membrane. The water behaves as if it has a thin elastic film on the surface.
Students, it is found that when a liquid is free from the external forces such as gravity, then it always tends to take the shape of a spherical drop. Now, why spherical drop? It is because for a given volume, a sphere has least surface area. Now, surface area of a sphere is 4 pi r square, which for a given volume is minimum. So what does it mean? It means that the surface of every liquid, actually the free surface of every liquid, it has a tendency to have minimum surface area. And in doing so, and in this respect, it tends to behave like a stressed membrane. So basically, surface tension is that property of a liquid by virtue of which it behaves like an elastic stressed membrane with a tendency to contract so as to occupy or so as to attain minimum surface area. So this property of a liquid surface is known as surface tension. Now let us discuss surface tension quantitatively. That is, let us find a way to measure the surface tension. For that, students, let us imagine a liquid to be contained in a beaker, and let us imagine an imaginary line, say AB, which is drawn on the free surface of a liquid. Now, in order to have minimum surface area, the two portions of the liquid, they will have a tendency to draw away from one another. It will be somewhat like this. These are the two portions of the liquid surface, right? It will tend to draw apart so as to attain minimum surface area, like this. So basically, the two portions of the liquid surface on either side of line AB have tendency to draw away from each other, as being indicated by these arrows. So what happens is, we can imagine that the surface film is cut along line AB. Then the film on either side of the line will tend to contract. This film, or the film, being prevented from breaking into two parts due to the force of attraction between the molecules. And which force I'm talking about? I'm talking about is the cohesive force of attraction. So again I repeat, students, AB is any imaginary line which is drawn on the liquid surface, right? Now it has divided the surface into two parts, isn't it? So on either side of line AB, and these two parts will have the tendency to draw away from each other. Now as a result of surface tension, what happens is these two surfaces will tend to tear apart, or it will tend to occupy minimum surface area, right? Now the film being prevented from breaking into two parts, it is entirely due to the intermolecular cohesive force that exists between the water molecules. The magnitude of this intermolecular force, which is preventing the surface from breaking into two parts, per unit length of this line drawn on the surface of the liquid, that actually gives us the measure of the surface tension. So mathematically, surface tension is quantitatively measured as the ratio of the magnitude of the force per unit length. This is the force which prevents the surface from breaking into two parts, right? And here one should note that there can be any imagined line. If we consider line AB, then more number of molecules will interact with each other. So accordingly, with the increase in the length, the magnitude of the intermolecular force will also increase, but the ratio will remain constant. Now if you consider this imagined line of shorter length, so here lesser number of molecules are interacting with each other. So here F dash, which is the magnitude of the intermolecular force acting on or between the molecules on either side of this imagined line CD, would be of lesser magnitude. But L dash is also less than L, F dash is also less than F, but the ratio remains same. That is, it will be F dash by L dash, right? So the length of the imaginary line which is drawn on this liquid surface, it is immaterial. Now students, in CGS system, surface tension would be expressed as dyne per centimeter, and in SI its unit is, unit of surface tension in SI, it would be equal to force, it is measured in Newton in SI, and length in meters. So its SI unit is Newton per meter. And the dimensional formula would be mL0 T to the power minus 2. This will be the dimensional formula for surface tension. Newton is kg meter per second square. Meter per meter will get cancelled. We will be left with kg per second square. So accordingly, dimensional formula of surface tension is m1 L to the power 0 T to the power minus 2. Now let us discuss surface tension on the basis of molecular theory. We need to understand the following points. Surface tension of liquids is actually a molecular phenomena, and the maximum distance up to which a molecule can attract some other molecules is known as the range of the intermolecular force. Suppose this is molecule M1 and this is another molecule M2 near its vicinity, right? Now the maximum distance up to which a molecule can attract some other molecules is known as the range. It may be represented by R. If another molecule is present beyond this distance from molecule M1, then molecule M1 will not exert any force on that particular molecule. So it is actually the maximum distance between the molecules up to which the molecules can interact with each other, right? A sphere of radius equal to the range of the molecular force about a given molecule as center would be called its sphere of influence. Now, if I take M1 as center and M1, M2 is equal to R as radius and draw a sphere over here like this, then it would be known as the sphere of influence of molecule M1. So, whatever molecules and whenever molecules are present inside that sphere, all those molecules will interact with molecule M1, isn't it? Any molecule which is residing outside that sphere will not interact with molecule M1. So, it's an imaginary sphere of radius equal to the range of the molecular force. That is known as the sphere of influence, right? With M1 as center. So, it will be the sphere of influence of molecule M1, right? And a thin film of liquid near its surface and having thickness equal to the molecular range for that particular liquid, that is known as the surface film. Actually, it is the surface film which is responsible for the phenomena of surface tension. Now, after discussing these points, we are able, or rather we are in a position to explain surface tension on the basis of molecular theory. Let us consider, students, A, B, C, D to represent the surface film of a liquid. Just now we have discussed surface film. It's actually having thickness. It is a film of liquid near its surface having thickness equal to the molecular range. We have represented molecular range by capital letter R. So the thickness of this must be R, which is the molecular range. So A, B, C, D represents the surface film of this liquid which is contained in this beaker, right? Now we have considered three molecules, molecule P, molecule Q, and this is molecule R, right? These are the three molecules of a liquid, and these are the circles which represent their sphere of influence. Its radius is equal to R, which is the range of the intermolecular forces. We have discussed, students, that a sphere of radius equal to the range of the molecular force about a given molecule is known as its sphere of influence. So these are the circles which are representing the sphere of influences of molecules P, Q and R respectively, right? So you can see from the diagram that molecule P, I've considered it to be well inside the liquid. Now this molecule P is attracted equally in all the directions by other molecules lying within its sphere of influence. So net force acting on molecule P would be 0. All these forces will get cancelled out in pairs. So resultant force acting on the molecule P, which is well inside the liquid, is 0, right? So net force on P, it is equal to 0. No net force is acting on the molecule P because it is attracted equally in all the directions, right? Now consider molecule Q now. In the case of molecule Q, more than half of its sphere of influence is below the liquid surface. Therefore, there are more molecules attracting it downward direction than in the upward direction. Now, this downward force is greater than this upward force. So as a result, what happens is molecule Q will experience a net inward pull, which obviously will depend upon the relative number of the molecules between the lower and the upper halves of its sphere of influence. So molecule Q, which is slightly placed below the surface of the liquid, will experience a net inward pull. So molecule Q will experience a net inward pull. It will experience a net downward force. It is because more than half of its sphere of influence is below the liquid surface, as it's pretty evident from this diagram. This is the portion of its sphere of influence which is inside the liquid, right? And only this portion, it's a minor portion which is in air. Now let us consider the case of molecule R. Now molecule R is considered to be lying on the surface of the liquid. Clear? In this case, students, the inward pull is maximum on the molecules such as molecule R, which is lying on the surface. Now it is because of the reason that lower half, this is the lower half of the sphere of influence of such a molecule is completely full of liquid molecules, while the upper part, it is empty except for few molecules in the form of vapor. So it will get attracted by its neighboring liquid molecules in the downward direction. So the inward pull is maximum on molecule R. So the inward pull or the force which is acting in the downward direction is maximum for those molecules lying on the surface, in this case for molecule R. Whenever we intend to move a molecule from the interior of a liquid to the surface, in that case an amount of work has to be done on it against this inward pull, isn't it? So this work done appears as an additional potential energy of the molecules which are lying on the surface of the liquid. So what we conclude is that the potential energy of those molecules which are lying on the surface film is always greater than that of the molecules which are residing inside or interior of the liquid. Clear? Now students, we are aware in the state of stable equilibrium, a system always tends to possess minimum potential energy. So therefore, in order to attain state of stable equilibrium, the system must have minimum potential energy. So as a result, what happens is the surface of this film tends to contract so as to have minimum surface area, so that the number of molecules in the surface film may be minimum. So this is how the concept of surface tension can be explained on the basis of molecular theory. Students, what we have discussed is all those molecules residing on the surface of the liquid experiences a maximum inward pull, and hence if we intend to bring a molecule from the interior to the surface, then we have to do some work against this inward force, isn't it? So as a result of this work done, it will get stored in the form of additional potential energy in the molecules residing on the liquid surface. So basically, the molecules lying in the surface film of a liquid experience an inward molecular force, and hence these molecules possess potential energy. Right? Now, we are aware, students, any system, it tends to attain the state of stable equilibrium, and in the state of stable equilibrium, the system, it possesses minimum potential energy. So this system will also tend to attain the state of stable equilibrium, and thus it will also tend to possess minimum potential energy. But we are aware the molecules on the liquid surface possess maximum potential energy, isn't it? So in order to attain the state of stable equilibrium, or in order to attain minimum potential energy, what the surface film does is, the surface film tends to have minimum surface area. So it contracts. It acts like a stressed membrane so as to occupy minimum surface area. Now, when the surface film attains minimum surface area, then the number of molecules residing in the surface film will also be less. And accordingly, the potential energy of the system will become less, and the system will attain the state of stable equilibrium. So students, the free surface of a liquid at rest, it tends to have the minimum area, and thereby in doing so and in attempting to do so, it behaves like a stressed membrane. And this is how surface tension can be explained on the basis of molecular theory.
So students, that's it for this particular session, and do join me in my next lecture then. Till then, do take very good care of yourself and keep watching my videos. Thank you.